Hi guys, how's it going this morning? Can you guys hear me okay?
Yes.
Good. All right. My 9 o'clock class couldn't hear me when we first started. I had to do all sorts of weird things with the Zoom settings and whatever. But if you can hear me, then I'm happy. All right. So let's just talk briefly about like what's coming up for us. So we have a test on November 16th. This is a Monday. I know I hate doing tests on Mondays. Normally I avoid doing tests on Mondays, but it just kind of happened that way with the syllabus with next Wednesday is a holiday. So November 16th is the Monday following that. So it's going to be our test day. So keep in mind, that's the day, November 16th, that we have a test. We also have our problem set. Number 2 is due. Okay. And then we have remaining homework problems. And then we also have our remaining classwork. Those are all going to be due on Monday, November 16th. So keep in mind, there's a lot of stuff kind of rolling right up, coming down on top of us here. Now, also, let's keep in mind what's going to happen today is we're going to keep talking about chapter 2.7. We're going to do more examples about rotations using quaternions. I've got a classwork page to keep working through. And then we're going to start talking about chapter 7, 2.7 part 2. We're going to start. And then on Monday, we're going to continue with chapter 2.7, this will be part 2. And then we'll work through classwork problems and other stuff. Okay, so it's kind of like a thing where you guys can ask me questions. We're going to go over stuff and and make sure we're getting it right. And then next Wednesday, we actually have a holiday. This is November 11th. There's no school. It's a holiday. Okay, so there's no school next Wednesday. So a week from yesterday, there's no school. And then next Thursday, right, we're going to have our review for our midterm. This is all in our syllabus, but I think it's helpful to write it down and kind of get it out there, make sure we all remember. So we're going to do a review for our midterm. If you guys can check on our modules page, I have a file up there called Additional Practice Problems for Midterm 2. Oops. Okay, check that out. I believe that's in next week's module that should be published. So you guys should be able to see that. If you can't download that file, email me and I'll go check it out to make sure that it's accessible for you. But we'll go over that on next Thursday. So a week from today, we're going to basically do a whole class that's a review. And then next week we can vote about having class on Monday, because I think last time when we had our exam, we didn't have class on that day because we had the exam. And this would be the same thing where we have an availability window on Monday, becomes available for 24 hours from Monday to Tuesday. But we can vote next week about having class or not on that particular Monday. Anyway, so keep that in mind. There's a lot of stuff coming down and a lot of things that are going to be due coming up. But today we're going to keep working on chapter 2.7, rotations in 3D using quaternions. And if we can, we'll start with, if we have time, we'll start with the using the Euler angles. Okay, it's just the rotation, using a rotation matrix. You'll see how more complicated it is. And then Monday we'll continue working on chapter 2.7. Okay, so kind of keep in mind there's a lot of stuff happening. Okay, guys. All right, so with that said, what I'm going to do is I've got my classwork page. This is the classwork. It looks like this, classwork 2.7 quaternions. We went through these problems yesterday. We were working through these problems, and I'm just gonna finish off this page here and then keep working through it so that you guys can see the solutions for how this actually works. Okay, and then and then we'll keep moving on from there. I scanned in the lecture examples notes for 2.7 part 1. So that's that was up on our webpage yesterday. So that'll help if you didn't capture all those notes to take a look at that. All right. So I'm just going to start working through these problems here, and then you guys can stop me as we go. But this is what's going on. Oh, and then question 7 should be you're rotating it 180 degrees. Okay, so I forgot to write down the theta on question 7, so it's 180 degrees. Or if you want to pick a different theta, you want to rotate it by a different amount, you can, but I'm going to do 180. Are you guys getting the same answers I did? Oh, I see. Wait, I made a mistake. This was negative. This is negative here. And this is 4/3. Doesn't change it too much. You guys getting the same thing that I got? Any questions on this one? This is classwork. Still thinking about it? Okay. So I'm going to put this away. Okay, this was the classwork for part 1. Okay, which we went through. We did the product of quaternions. We added the 2 quaternions together. And then we started rotations using quaternions. Okay. So I'm going to start thinking about part 2, which is our rotations in 3 dimensions, but using angles. Okay, so we're still doing rotations in 3D. 3D, and we're going to use, I can spell using angles. These are the Euler angles that we had talked about before. Okay, so this is like the long method where I said this one is computationally more expensive. You have problems where we can end up erroneously, mistakenly canceling one of our degrees of freedom. Okay, so let's just write down, let's remind ourselves, if we don't use quaternions to perform rotations in 3D, we need to think about angles. We have to think about all the angles that are going to be like, we're going to rotate 180 degrees around something, but then we have to break that angle up into like its X component, its Y component, and its Z component. So let's kind of draw a quick picture where we can think about what we're doing here. So here's our X, Y, and Z axes. And then I'll do this in different colors so you can visualize this better. So we've got something that we're rotating around. Say, for example, we've got some kind of line. It's linear, right? It passes through our origin. Okay. And then I've got, do this in green. I've got the vector V, okay, which I want to rotate V some angle measure around this thing here. So I'm going to rotate, we're going to rotate around by theta, around RU by theta. So this is like theta radians or theta degrees. This is how much we want to actually rotate around. And then what we're going to get out of it is, we'll call it V prime. This is our rotated vector. Okay, so now let's write down what we have here in our pieces. So RU is the line to be rotated around. Okay, and then this u is going to be a unit vector. Okay, when we actually do this, we need to make it, we also have to use a unit vector. Okay, so remember when we do stuff, we're going to be converting things. This vector here gets converted into a unit vector. V is our vector to be rotated. Theta is the rotation amount. Angle. You can think about this. This is the amount to be rotated around RU. Okay. V prime is our final rotated vector. Okay. And then if we do this, I'll just do this in black here. We can consider, I'll put a point here. I'll do a point instead. Say we wanted to rotate a point instead. So we're rotating a point instead of a vector v. Like say, for example, I've got a sphere and it has a center, but I want to rotate this whole sphere around something in 3 dimensions. So what I'm going to do is I'm going to just take a look at my sphere as that center point. I'm going to take that center point and I'm going to rotate that around something in 3D. And then I'm going to build up my sphere again. Okay, so I can rotate a point around this just as easily as I can a vector. Okay, so again, we have to convert our u into a unit vector. Okay, so remember, we take our u, whatever our u is, I divide it by its magnitude to give me its unit vector. Okay, so our rotation matrix, it's going to end up looking, I'm going to first give you the equation and then we're going to fill in the blanks and you'll see how complicated the matrix is. So we'll call it rotation around u is equal to the projection onto the unit vector plus the cosine of theta times the projection perpendicular to that unit vector, sine of theta, and then this, I'll tell you what this is in just a minute, times our left cross product. So let's write down what these things are. So this is the piece that we're going to be working with. We're going to fill in the blanks on what all these things are, but first let's write down what they are and then we'll tell you the math on them. Okay, so this is going to give us our final value, our final answer, which is a rotated point or a rotated vector. This is the projection onto. I keep writing it out like this, but often our books, our notes and stuff will write it like this. So U with a little hat on it is a symbol for our unit vector. Okay, but I'll keep writing it out like what it is, just so that you know that we could write this in shorthand. If you look at your notes, it's going to look like this. So this means perpendicular, right? So remember how we do this, we're projecting onto the plane that's normal to the line that we're rotating around, because we're using projections in order to do this, right? So projecting onto the plane that's normal to this line that we're rotating around. That's what this P projection, this projection onto U perpendicular means. And this is a left cross product. Okay, by our unit vector. All right, so that's a lot to keep track of, right? There's a lot of little pieces, but so I'll let you guys finish writing that. I'm gonna make some notes and then I'll give you the matrix for what things are. Okay. So some things to note are this. When we're going to break our vector v into a part that's parallel to our u, our unit vector, and a part perpendicular to our unit vector. Okay. So the part that's parallel to our unit vector stays the same under rotation. This is our projection. Oops. Our projection onto that. The rotation part that's perpendicular to our unit vector is really the rotation in the plane that's made up of, that has this unit vector as its normal, okay? And this gives us the, that comes from our cosine theta and our sine theta, okay? All right, so just some notes to think about. And then what I'm gonna do is we're gonna let our unit vector have components A, B, and C, okay, for X, Y, and Z. Our X, Y, and Z components for our unit vector are A, B, and C. It's important because I'm going to use A, B, and C in this equation here. Okay, so now I'm going to give you this matrix for rotation around this line. And I'm going to assume that I'm going to start calling this U hat because it's getting too complex to do the U divided by its magnitude. So I'm going to start calling it U hat. But remember, U hat and U vector divided by its magnitude are the same thing. Okay, I'm just going to start calling it U hat because it's easier. All right, so here's our rotation matrix. You're going to see there's a lot of pieces to it. I'm going to have to write them to fit them onto the page. I'm going to have to write them a little bit off-centered. So rotation, it's going to be, okay, a squared plus cosine of theta, 1 minus a squared. So this is my X column. This is my first column. My second column I'm going to write down here. My third column I'm going to write down a little bit below that just so I have room. So there's my first column. My second column, I just don't have room on the paper to write them all out across. That's my second column. And my third column I'm going to write down here. Okay, so there's a lot. Right, it's very expensive computationally, right? There's a lot of cosine calculations, sine calculations. Those are more expensive. The b squared's all a lot of multiplications and stuff. And I'll give you the individual. I'll let you finish writing that, and then I'll give you the individual matrices. Okay, so our individual matrices go like this. So the projection onto u hat, which is our unit vector, is equal to a squared ab ac, ab b squared bc, okay, remember u hat is a, b, and c components, okay? Cosine of theta times the projection onto the perpendicular of our unit vector is equal to the cosine of theta times our identity matrix minus this right here. Our sine of theta times our left cross product looks like this. Okay. So that's where these matrices come from. So we'll work through first example here. We only have example 1 to work through on here. Okay, so I've got my lecture examples. This is 2.7 part 2. I'm going to work through the example number 1. All right, so this is the same thing that we did with quaternions, but now we're going to use our rotation matrix with just using angles. Okay, so again, let's come up with, this is our u, so let's come up with our u hat is going to equal to u all over its magnitude, which is 1, 1, 0 by radical 2. Okay, so my A, B, and C get assigned this way here. Let's see. My theta equals 180 degrees. Let's just prefetch this. So the cosine of 180 degrees equals -1. The sine of 180 degrees equals 0. So let's fill out our rotation matrix. Okay, given our A, B, C, and our cosines and sines. That's column 2. There's column 3. So doing this all together, putting it all together, adding it all up is going to give me if I had rotated around something like 30 degrees or 34 degrees or something odd like that, then I wouldn't have so many ones and zeros. I would be adding up all these little nitty gritty decimals. Okay, so I kind of chose an easy angle to rotate around because cosines and sines are nicer when you're right along the axis there. Okay. All right. And that's, I'll scan in the lecture notes for that. And I'll put that up online later today. Okay. You guys have any questions? Okay, I actually have to tell you, I'm actually, let me just do this really quick.